semantic segmentation. And so does anybody know the standard dictionary meaning of semantic? Semantic. Huh. What is the meaning of semantic? The true meaning. Okay. Yes. And something more simpler. So the true meaning necessarily always has to be the simplest of the meanings. Like whatever you say and what it means at face value, that is what it has to be. Okay. So semantic segmentation is something which in general is a simple segmentation case. So a simple segmentation on an image would essentially imply that every single point in that image is classified into certain segment over there, and any point should not belong to two segments. It should belong to any one of these segments. So it's like an exclusive relationship in terms of classes which you will have for a semantic segmentation. Now by definition, this is something it should give. So this is an image of a bedroom with a bed. You have a mirror over here, you have some painting over here, there is a window over here. Now every single pixel over here needs to be annotated as belonging to a certain class. Okay. Now generally all of these data sets which you will get down for semantic segmentation, they would have a color which you see, and now that color is just a label information. So it's called as an indexing color space. So you have an index, an integer value which is the class label which is given, and each class label or an integer is associated with a RGB value, and that's how they show it up over here. Okay. Similarly, this is another image where you have a center table, you have sofa, there is a some sort of a window over here, there are some plants kept down, and you have each of these appropriately annotated. Okay. Now the difference which comes down is that in some of these data sets all furnitures are grouped into one, you don't have a different class for your sofa, etc., etc. And in some of them, like a sofa is a different class, a bed is a different class, a chair is a different class. Based on which particular data set you are going to do it, it will come down. Then major part of semantic segmentations today get used in autonomous driving in a very significant way. Now in autonomous driving, the bigger one is the Oxford Robocar dataset. So if you want to download that one, that is 3.5 terabytes of data. 3.5 terabytes of data. How long will it take to download? Huh? 3.5 terabytes of data. How long will it take to download? What is the largest file size of the movie you have downloaded? 49 GB. Which movie? Huh? Okay, untouched Blu-ray disc format is what you have downloaded over there. So that I would assume that it's a uncompressed 4K UHD form in which. So I mean, you will have to get down a bit more technical when telling me. So Blu-ray, I would assume it's a 4K UHD. Was it so? It was a 4K. Okay. So now that's how much? 39 GB. 40 GB. Okay. And now I am telling you that there is one data set which is 3.5 terabyte. How much time will it take to download? Array, do that, how much time it took to download your 30 GB and then tell me how 40 GB and tell me how much time it's going to take you to download 3.5 terabytes. But seriously, where did you get 50 Mbps? So that's an issue. The point is that on the other side also you need to have an upload link speed for a single client at 50, but you're doing a torrent or something? He did something he's not going to tell. Huh? Okay. Oh, okay. That's a Hungarian hosting site, I remember. See, the definition of legality, illegality is too debatable. I won't comment on that. Whose ever property, that guy is the most worried about it. about somebody else using their property. But nonetheless, so the point is that in a standard case you can figure it out. I mean, how long it takes for you to download a video, and your connections are not 50 Mbps for sure. I mean, your general hostel level connections are something which are curtailed at 100 kbps itself. Otherwise, you're going to bottleneck the whole thing. I mean, our whole campus-wide total entry-exit bandwidth is, I think, 10 Gbps or something is what is our campus now. So you can go on the CIC's website and actually look into it. I think it was 10 with the all pipes which we have. Now, the issue which will come down is that you will have a rich part of the data, but then on the other side of it, you look into this one, that every single pixel being densely annotated. So if I have an image of 1024 cross 1024 pixels over there, so I essentially get down 1 mega, 10 to the power of 6 number of pixels which are densely annotated. So the number of samples which comes per image is itself a million. So now if you are doing a binary cross entropy or any of these laws, then it's a million sample binary cross entropy calculated per image itself. That's a compute challenging problem. Because by now you know how to calculate the compute complexity around your loss functions, around your layers and everything over there. So loss functions you can derive it out. I'm not going to derive loss function compute complexities. So now you can pretty much come down to the point of how complex that is going to be. Now, if we take the first part of the problem, which is what is and how will you do it with a neural network. Okay. Now, give me some assumptions of how can you do. So I essentially said that you have this whole network, you have this whole image, and you are supposed to classify every single pixel in that image. So how will you do that? So essentially you don't have that only one single neuron. You are saying that you will have a 2D map. But then this 2D map should look of the same size as the original image. But then if you are keeping on doing padded convolutions, then you are going to lose out something on the side. Deconvolutions, yes, a very good idea. You can have deconvolutions, you can have actress convolutions, you can have up convolutions, you can have unpooling, any of these things which you can do over there. Okay. So let's get into some of these standard ones. Now, one of this is what is called as a U-net. Now, U-net essentially gets its name from the structure that it looks like a U. That's the truth. I'm not joking. I mean, that is what Olaf, who is the PI for this particular one. Where is Olaf? Yeah, Olaf over here, the first guy. Now, that's what is Olaf's definition around this whole point. Now, what this does is interesting. So you take an input image, you have a set of convolutions over here, and these almost look like a VGG type. So it's a bank of convolutions which will not downsample it out, but you will have the same size of a activation map which is propagating. So the XY size remains the same. From here you do a downsampling over here. Now it's not very clearly visible, but if you can somehow see this one, that there is a red color max pool operation 2 by 2, that is what is happening. And this is what is going to bring down the size by 2 by 2 over here. Then again you have convolutions, then again you do the same thing, you drop it down, drop it down. Over here you get down something like which is very small in size. It's almost like a pipe which comes up. From here what you are going to do is you will do an up convolution. An up convolution is something like an unpooling operator or just a interpolation kind of an operation over there. Now they do this interesting part that whatever was the activation over here, that gets stretched and you concatenate it over here. So essentially there was 512 activation channels over here. You pulled all of them and concatenated. So you got down 512 channels plus you concatenated another 512. This made it 1024. Then you run your standard convolutions, you go up. Every time you do an upsampling, what you do is you concatenate this activation from a matching downsampling layer over there and keep on doing over here. So every time you will see this white part over here, and that block is that repeated part which keeps on going on and on. Now there is a distinct advantage which you get as a result of doing this. One of the major advantages which you get is that there will be a loss in activation due to downsampling. So every time there is a downsampling, you basically replace 4 numbers by 1 number in a 2x2 downsampling. Now as a result of this, you are going to lose out some significant number. 3 numbers are lost out. Now how do I reclaim those 3 numbers? So we can guess what were those 3 numbers as we had seen in the unpooling time. but then there is no exact value of what are those 3 numbers. Now what this will screw up in a big way is the sort of clarity of an image, or say how sharp are the edges or boundaries or something over there. Now when you are able to bring in this high resolution activation map, that actually carries a part of this information together over there. So when downsampling and going down, this is where the mixing happens across all of them. This is where sort of like the unmixed or locally unmixed information which you are going to put down, and together you come to this output segmentation. Now here this tensor size of this output segmentation is the same as the total number of classes. So here this was a 2 class classification problem. There is a foreground or there is a background and nothing else. So they have 2 channels. One channel which gives you all the foreground, one channel which gives you all the background. Now you can pretty much say that essentially there is a set of 2 neurons which corresponds to every single pixel location, and you have a matrix of such a set of 2 neurons over here which is created. Now look into one big advantage is you have just a set of convolutional kernels in one standard convolutional neural network which can work on every single location of that image, and this is again a property of convolution itself, which says that this is supposed to be a space invariant operator. So as in convolutions from your mathematics, it was supposed to be a time invariant operator or something. If you have a background in electrical sciences, you know that convolutions are time invariant operator or linear time invariant, sometimes what you call in an LTI system. Here this becomes a space invariant operator, and that helps you in coming down to this one. Now when you train that, it becomes really interesting how these people had trained. So you had an image, the quality is really horrible, and that's because the original image's contrast itself was very low. So these were scanning electron microscope images of epithelial cells. So epithelial cells are like cells which make up the outer or the inner part of your body, and what these guys had done is they took a Johnson's bird ear dewaxing buds which you get down, you put it in your mouth and you take a swab. Have you done that ever for any medical test? Swab of the mouth, nobody did it. So you take a swab out over there. Now with your saliva comes out a lot of cells which look like very flat lotus leaf like structures over there, and then they took a scanning electron microscope over here. Oh, by the way, is there a scanning electron microscope in the campus? Yes. Where? CRF, good. The other guys did not even know. We have an electron microscope in the campus. So if you have studied that in your science books but never knew how it looks like, then you should be making this attempt to go and see it, because we are one of those very few institutions in the world which has a scanning electron microscope on campus. These are like rare things which you rarely get to see. So they took these images out over there, and then these were like manually annotated segments. Now the task was like each color which you see is basically one different cell over there. Every single cell, as in a biological cell, every single cell has a different color given down, and the task was that you have to find these segments out very clearly. Now one issue, this is the point which you are raising, that because you are finding out say binary cross entropy at every single location, now there can be some spot errors over there, and because of the imbalance in class, if you look into the number of cells versus everything which is not a cell, which is these boundary areas in black, that is much lesser. Most of them are cells. So now your error will somehow become skewed if you are trying to take a BCE error over there. So what they did is, the idea was that we take in a weighted binary cross entropy, and the weights were taken down to the point that if it makes an error in the borders or whatever is not a cell, then penalize it significantly. If it makes an error in between the cell, then don't penalize it significantly. So, and that kind of a weight is what is used over here. Now in order to derive this kind of a weight, nobody manually sat down and actually derived the weight. There was a very simple morphological operation in image processing which was used for doing that, and that's what's called as a top hat transform. So if you ever take a image processing class, just read about binary morphologies and top hat transforms, and you will get down how to come to this kind of a loss function. So what this is going to say is that all the points which are exactly in between these white regions are which will get a very high value, and as you go towards these white regions you will get a low value, and anything which is inside the white region will not have any, will basically have the standard DC value of 1 over there, or unity weights given down. So that was a kind of thing which they had used and trained this whole network using binary cross entropy as a loss. and they could run up this segmentation. So these were some examples which they got down. So this shows basically the segments which were obtained for this cell class over here as well as over here. Now here generally you are able to see only one of them on is a good contrast, but then there were a lot many more of them as well which got segmented out very properly. Yeah. Yes. Yeah, yeah. There is a variant. So UNet is what came in 2015 based on some research done in 2014. Residual Nets came in 2017. Deep Residual Nets came in 2018. So there was a scale in which things came. Uh, Not a ResNet, but a DenseNet. DenseNet will have all the connections. So today we have a lot of networks which actually make use of both of them. So there is one such network which we have in our group which we had proposed out that is like which has a significant lower compute complexity but can achieve these things in a much better way. So let me come to the next network and then I am going to tell you like how we scale up. So there are a lot of takeaways which you can take. So in 2015 the major issue was like generally people would have gone down and then come up, and then you lose out on these high frequency components or very detailed in space. So one thing which they found out is let's just concatenate the activations. There can be other options like you add the activations as well. That would be your residual kind of a connection. So you can pretty much do it, but then that kind of an operation was not that well practiced in 2015. It's just a historical part, nothing more. Now when they came up with this whole thing, so this was the performance which was reported for UNet. Now these are two different kinds of cells on which it was done. I don't want to get into cell lines and explaining you that part of it, but just that there are two different categories of images on which it was trained and it was tested out on two different categories of images itself. And now you can see that difference in terms of its dice coefficient which it comes out. So this was a dice coefficient which was reported. So the closer it is to 1, the better it is. And you have a significant improvement over all the previous methods. Now the second best was something which made use of a neural network in order to do it. All of these were classical image processing based methods. So KTH is from KTH in Sweden, IMCB I don't remember. House is most likely the University of Houston group over there which was doing it. So these were their scores which they had reported in this challenge for cell segmentation in 2014, and then this was what they reported out in the paper together over there. Now this is what typically consists of a benchmark itself. So what you have is all the prior people and whatever their points were and where you stand. Now if you invert this one, that you have the best on top and then everything else, then that is what is called as a leaderboard which you would see today. And I still call this as a benchmark because you don't have multiple metrics, you just have one metric of accuracy for each of them against which you are comparing. So if you have multiple metrics on which you are comparing, then you get a leaderboard. So a leaderboard or a scoreboard like what you see for a cricket match. So for every single player you would get down a scoreboard. Now that does not only have the number of runs scored or the number of wickets taken, it will have all of these properties over there, whatever was your run rate, what is your variation in run rate, and all of these metrics which would come down. So that is the difference between a leaderboard and a benchmark which you would have. Now the next network which I would speak about is what is called as a Signet. Now Signet is interestingly what these guys did was, if you look at this part, it looks almost like a pyramid, and this is what we generally have a term called as an encoder. That's where this term comes down. Now this is encoder because it basically takes in an image and brings it down to a latent space which will have some information in reduced number of codes present over there. Now this structure, if you can recall something, then this is the same as a VGG16 part without the fully connected network over there. And in fact what they did was they took a pre-trained VGG16, just truncated the two 4096 layers over there, the fully connected layers, and kept the remaining of them. So you had the weights which were already tuned. You did not need to worry a lot about tuning the weights. It was a trained model over there. They created this side of it, which is a decoder, which is a match structure. So you have almost a matching in terms of its sizes and everything which goes down, and number of convolution layers as well. Now in order to go from here to here, in case of a unit you had a unpooling which you were doing, a max unpooling. Now here they do, so in case of a unit, that unpooling which it was done is not an index passing unpooling, which is whatever is my value I just replicate it by 2 by 2 is what a unit standard had. Here they were actually doing a index matched unpooling, which meant that whatever was the location from where my max had come down, I will place that value back into that particular location over there. Okay. By way of this, what you are able to achieve is that you don't get a smearing about in the whole image. You have much detailing present around your borders and boundaries where your majority of changes and activations are coming place. Now that helped them in actually getting down a much denser and deeper output as well. Okay. Now I come back to your point. So what you can do is, you can do a max unpooling, you can do an activation concatenation as well, and you can create a new network. But then I will not let you have the fun of creating that new network, because 2 years ago we made that network. So there is another network which we called as Signet, and that's basically a Signet S and a union with a standard unit. So that was what it was called as a Signet unit mixture. I think that's what, from where it got the name. And then accordingly you are able to get down your output. So later on point of time in applications I will speak about the Signet part and the reduction in the complexity of operations and everything which happens over there. Now typically this network had a larger advantage. So though you have many more parameters in the encoder over here, but because this encoder was trained, so it took much lesser time in order to train the decoder part over there. VG16 is a very bulky model, but because your model was trained, so it takes less time to train this decoder part over there, and that made it really faster as a process to do it. This was done typically for scene segmentations over there. It's a standard PAMI paper from 2017. It was based on a model which was in CVPR workshops in 2015, I believe, 2015 or 2016. There are two ways of doing it. You can freeze it, but so what we do is something which is called as a hot restart condition. So initially you would freeze these weights, then train this when it hits a saturation bottom, and there are whole issues like you keep on changing the learning rates and everything as you keep on going, and once you see that it hits a plateau, it does not go any forward, then you unfreeze these weights and you keep on training. But together this training does not take anything more than 30-40 epochs. So you would see that in 1 or 2 epochs itself it hits that point over there, and together you can do that, and I think 30 epochs is where it is max what it needs in order to get to that point over there. The reason why they would not need a lot of epochs is the number of errors you will calculate over here is for a pixel basis, so that itself is a million. So I have a million calculations per image, and I have a small batch size of 10 or 20, I am already doing a large scale update over there. So that's an advantage which you get with semantic segmentations. So these are some of these examples of how they were performing. This was the original image, this is the ground truth which was there, and these are the predictions which came out over there. There were still issues, like there were these discontinuous points which this was tending to miss, but otherwise, like in a general way, majority of the segments were coming out in a very good way, and you had most of the structures present as well. This was what they had extended on standard scene images, and then this is from a different data set. I think this was a MS Coco semantics data set on which it was done. So this is from the Kitty data set, which is a street driving data set from Germany. University of Kaiserslautern does that, and this one is from the MS Coco Common Objects Semantic Segmentation. So this is from Microsoft over there. So that's where I come to an end for semantic segmentations. Now tomorrow we are going to do a bit of deep diving into semantic segmentations more. So I will come up with cases of how you need to create new kind of loss functions in order to do that, and then what are the challenges around with semantic segmentations and it's a very application specific. So if you don't have an application, it becomes hard to tell you exactly where that whole issue comes down, and then I will show you like how you can extend that for doing something which is called as a regression problem, or what we also call as super resolution. It's the same kind of a network, encoder decoder, but you can use it for a lot of other problems as well. Okay, so we stop.